So let us start with something you have probably felt but maybe never named. Let's say we build the track assistant from the last video. The user asks a question and our app does its job. It retrieves 20 chunks, adds the system prompt, the chart history, all of it, and sends one request to the model and then nothing. For a few seconds, nothing streams. The user is just watching a spinner. Then the first word appears, and after that, the rest of the answer comes out fairly steadily, token by token. So here is the small mystery. The first token took, let's say, 6 seconds, but token 50 came back in a few tens of milliseconds. Basically, instant next to the first one. Same request, same model, same GPU. So, why are these two different? And at high level, the answer is this. On the API side, it looks like one request. But inside the model server, it is not one job. It is two very different jobs glued together. One is a reading problem, the other is a memory problem. And honestly, the strange part is that second one. Once that first token comes out, the GPU is barely even doing math anymore. Most of the time, it is just waiting on memory. And that is the thing we really want to understand. So in this video, we are going to open up that server and actually watch what happens to a prompt after it arrives. Prefill, decode, the KV cache, batching, all of it. And by the end, when someone says inference is slow, you will know that question is too vague and you will know exactly which clock to look at. Okay, so let us follow that one request in. First, it sits in a queue. Then it gets tokenized. The text is broken into tokens. The little pieces the model actually reads. Our RAG prompt with 20 chunks and the history, let's say that is around 8000 tokens. And then a scheduler decides when it runs on GPU, the graphics processing unit, the chip that actually does the model's math. Now, here is the part most explanations skip. Once it reaches the GPU, that single request becomes two different kinds of work. First, the model has to read all 8000 prompt tokens and understand them together in one pass. This is called prefill. This is the part that happens while the user is staring at the spinner. Nothing has streamed yet because the model is still reading. Then, once it has read everything, it starts writing the answer, but it cannot write the whole answer at once. A language model generates one token at a time. It predicts the next token, then the token becomes part of the input, and it predicts the next one, and so on. This loop is called decode. This is why the answer streams. It is not a UI animation. The model genuinely is producing token 1, then token 2, then token 3. So already we can name our two clocks. The time until that first token appears, that is mostly prefill. And the time between each token after that, that is decode. One request, two jobs. And honestly, almost everything hard about serving comes from the fact that these two jobs want completely different things from the GPU. So let us look at prefill first. We have 8000 prompt tokens, and here is the nice thing. They are all already known. The model does not have to wait for any of them, so it can process them together in parallel as one big matrix multiplication. And a GPU loves that. Big parallel matrix work is exactly what it is built for. So prefill actually keeps the GPU busy. The compute is full. Now, decode is the opposite. In decode, the model produces one token per step. So instead of a big wide matrix, each step is this thin little slice of work. One token going through the whole model, and the problem is not the math itself. The math is tiny. The problem is what it has to read to do the math. To produce even one next token, the GPU has to pull the model's weights and it has to read the memory of everything that came before. That is a lot of reading for one small token to compute. So at high level, prefill is compute bound and it has plenty of work to keep the GPU's math units full. Decode is often the other way. In practice, it becomes memory bandwidth bound. The GPU is mostly waiting on memory reads and its math units sit half idle. And I want to be careful here. This is not a law of physics. Batch size, context length, the hardware, all of that can shift it. But in normal serving, that is the pattern you see. And there is a clean way to hold this in your head. The first token is a reading problem. Every token after that is a memory problem. And this asymmetry is not just some internal detail. It even shows up on your API bill. If you have used any of these APIs, you would have seen two prices, one for input tokens, one for output tokens. And across the big providers, output usually runs a few times more than the input, commonly around 3 to 5 times, and even more on the newest flagship models. And that lines up with exactly what we just saw. Input tokens are prefill, cheap per token, parallel done in one pass. Output tokens are decode, one at a time, each one paying to read that whole memory again. So, prompt tokens and output tokens are really two different currencies. And one more thing before we move on, because it is the reason batching even matters. Remember, decode reads all of the model's weights just to produce one tiny token. So if only one sequence is running, most of the GPU's math units are sitting idle during that read. But if we run, let's say, 64 sequences together, they all ride on that same one weight read. And suddenly that idle math is doing real work. That is why batching buys us throughput. And it is also why, for the rest of this video, we keep fighting to fit more sequences into memory. So decode reads the memory of everything before. Let me make that concrete because this memory has a name, the KV cache. And it is the single most important object in this whole video. Here is the why. When the model generates a token, that token has to look back at every previous token. That is attention. And to do that, each earlier token has some computed state. Now, without a cache, the model would have to recompute that state for all 8000 previous tokens on every single new token. That would be hugely wasteful. So instead, the first time we process each token, we compute that state once and we keep it. Then every future token just reads it. That stored state is the KV cache. And one thing I want to say properly, because a lot of explanations get this loose. The KV cache does not store the previous tokens. It does not store the text. What it stores is the keys and the values. Two vectors are the model computed from each token at every layer. So it is this model's internal attention state layer by layer. Same token in a different position can even have different state. So please do not picture it as a little box of saved words. Picture it as the model's working memory of the conversation so far. So now the loop is complete. Decode reads the KV cache, predicts one token, appends the token to own K and V to the cache, and repeats read, predict, append, read, predict, append. And here is the cache that sets up the entire rest of the video. The cache is not free, it grows. Every token we add, prompt or generated, adds more state to that wall. Okay, so the cache grows by how much? Let us actually do the small multiplication because the number is the whole point. For each token, the cache stores a key and a value, that is 2. And it does at every layer. And for every KV head, a model runs attention through several heads. Let's say 8 of them, each one looking at the sequence a little differently. And each head keeps its own key and value, each one of those vector of some dimension in some precision. Let's say 2 bytes. So per token it is 2 times the number of layers times the KV heads times the head dimension times the bytes. Multiply a token count on top of that, and that is your cache. And the real paper numbers are honestly a bit scary. The paged attention paper works this out for a 13 billion parameter model, OPT 13B, and it comes to roughly 800 kilobytes of KV cache for one single token. So one request at its full 2048 token length needs about 1.6 gigabytes of GPU memory just for its cache, just for one user. So now put it on the GPU. Let's say a 80 GB card. A big chunk of that is the model weights sitting there permanently. A little more is scratch space for the current step, the activations, and what is left is where the KV caches have to live. And here is the reveal. Batch size, the number of requests you run together, is not really how many users. It is how many live tokens worth of KV state can I fit in that leftover memory. A few users with very long RAG prompts can eat more memory than 100 users sending tiny chat messages. So the thing that limits how much you can batch, and batching is how you get throughput, is not compute. It is this growing memory object. The KV cache is the wall. And once you see that, every trick in the rest of this video is really the same trick. How do we fit more useful tokens against this wall? So we need to batch, and the obvious way, the way a normal web server batches, is collect a few requests, run them together, return them together. And for most systems, that is completely fine. But for generations, think about it properly, because it breaks in a way that is easy to miss. Let's say four requests come and we batch them. One of them is a short answer, 10 tokens. Another one is a long one, 200 tokens. With normal batching, the whole batch runs together until the last one is done. So the 10 token request finishes almost immediately and then just sits there, trapped, doing nothing, waiting for the 200 token request to finish. Its user is done. The answer exists, but it cannot leave the batch. This is the head of line blocking. Short request stuck behind long ones, and any new request that arrives has to wait for this entire batch to clear. So, quick, what would you do here? The shortest request is finished. Its answer is just sitting there ready. Do we really keep it locked in the batch, waiting for the longest one? Or is there a smarter move? And the fix, which came from a system called Orca, is to stop thinking in whole requests. Instead, schedule at the level of a single step. Run one token step for the whole batch. Then, right after that step, check is anyone finished. If yes, let them leave immediately. Return their answer, free their memory. Is anyone new waiting? Pull them in. Then run the next step. This is called continuous batching or iteration level scheduling. And the mental shift is the important part. In a normal server, the batch is a group of requests. In LLM serving, the batch is a group of next token jobs. And its membership changes on every single tick. Requests are flowing in and out constantly. And nobody waits for the slowest one to finish anymore. So continuous batching lets requests come and go, but there is still a problem sitting underneath it, and it is about how the cache is stored in memory. And this next part is honestly the biggest idea in the video. Here is the old way. A request KV cache was stored as one contiguous block, one solid slab of memory. And the trouble is, we do not know in advance how long the answer will be. So the system would reserve the maximum, let's say room for 2048 tokens upfront, just in case. Now let's say a request only ends up using 80 tokens, the other roughly 1940 slots reserved, sitting empty, but unusable by anyone else. Multiply that across every request and it wastes a huge amount of memory. And this is not me exaggerating. The real paged attention paper measured real systems and found that only about 20 to 40% of the KV memory was actually holding token state, and the other 60 to 80% was wasted, reserved but empty, or fragmented into gaps too small to use. So, what is the fix? And the fix is borrowed straight from operating systems, virtual memory, paging. Instead of one contiguous block per request, break the KV cache into small fixed size blocks. Let's say 16 tokens each. The blocks can sit anywhere in the memory, scattered in any order. And we keep a little lookup table, a block table that remembers for each request which physical block hold its sequence in order. So the request still sees a clean ordered cache, but physically the memory is packed tight with almost no waste. And I want to be precise about analogy. The blocks live in GPU memory. It is not swapping to disk. It is virtual memory for the model's memory of the conversation. That is the whole idea. And the payoff is huge. That same measured waste drops from 60% down to 4%. So you can fit far more live requests in the same GPU. The VLLM system built on this reported 2 to 4 times the throughput of the previous best systems at the same latency, same hardware, same model, just a smarter memory allocator. Okay, so now we have continuous batching and page memory. But here is a subtle production problem that shows up the moment you mix real traffic. Remember, prefill and decode are sharing the same GPU worker, and prefill is this big, heavy, compute hungry job. So let's say we have a bunch of users happily streaming their answers. Decode is ticking along, one token every so often, nice and steady. And then one new request arrives with a giant 800 token rag prompt. If we process that whole prefill in one shot, it's like truck pulling into single lane road. That one big prefill hogs the GPU for let's say the duration of 8 decode ticks, and during those ticks, everybody else's stream just stalls. Their tokens stop coming, their answer freezes mid sentence, and the user has no idea why. So the fix from a system called Sarathi is chunked prefill. Instead of doing the whole 8000 token prompt at once, split it into smaller chunks. Do one chunk of the prompt, then let some decode ticks run for everyone else. Then another chunk, then more decode ticks. So the long prompt still gets read. It just gets read in slices, and it no longer freezes everyone else's stream while it does. And the way I think about it, chunked prefill is the scheduler being polite. It is saying, I will read your long prompt, but I will not going to make everyone else wait in silence while I do it. And this connects right back to RAG, right? Every extra chunk you retrieve and paste into the prompt becomes prefill work. So on the serving side, just add more context is never actually free. So prefill per token is cheap, but a long RAG prompt is a lot of these tokens. So in total, reading it gets expensive. And that raises a natural question. What if two requests share the same beginning? Do we really have to read it twice? And often, no. This is prefix caching. Let's say you have a long system prompt or a big reference document that goes at the front of every request. The first time we prefill it and build it KV blocks. But instead of throwing those KV blocks away, we keep them. So the next request that starts with that exact same prefix can just reuse those blocks. It skips the prefill for the shared part and only does the new work for whatever comes after. System prompts, few short examples, a document you are asking many questions about, a multi-turn chart where the history keeps repeating. All of those benefit. But there are two guards here, and they matter. First, it has to be an exact token prefix. The model is matching tokens, not meaning. So if even one token changes early, a different date in the system prompt or in RAG, the retrieved chunks pasted in different order, the shade prefix stops right there. And everything after it has to be prefilled again. Two prompts can look almost identical to us and still share almost nothing. And second, this is the one people get wrong. Prefix catching helps prefill. It does not speed up generating new tokens. It does not touch decode at all. So if your slow part is the streaming, if your bottleneck is decode, prefix caching will not save you. It is not a magic make inference fast button. It is specifically we already paid to read this prefix, so let us not read it again. Now I have shown you the core mission: prefill, decode, the KV cache, batching, paging, chunking, reuse. And honestly, that is enough to understand almost any serving system you will meet. But I do not want to pretend the story stops here, because there is a whole research field pushing on this, and it is worth a 60-second map, just so that you know the terrain. Not so you learn every algorithm, and the important part is this: almost every one of these is just fighting the exact same wall we just built, the KV cache. They just attack it from different sides. One side, make each token's cache smaller. Modern models are literally designed for this now. Grouped query and multi-query attention share state across attention heads, and DeepSeek's multi-head latent attention compresses it further. They reported around a 93% smaller KV cache. So sometimes the model architecture itself already made the cache cheaper before serving even starts. Another side, keep fewer tokens, evict the ones that seem unimportant under a memory budget. Another, move the cache somewhere else, offload cold blocks to CPU memory at the cost of moving data around. Another, split the two phases entirely on two different machines, prefill workers and decode workers, since they want different hardware, and then ship the KV cache between them. And one more, speculative decoding. Draft several tokens ahead with a small cheap model, then let the big model verify them in parallel. Which chips at that? One token at a time. Bottleneck. And the big model still decides the final tokens, so lot of branches. But do not get lost in the names. The point is just this: when this many independent systems all grow the same organs, that is a signal. These are not random optimizations, they are the shape of the workload. Okay, so let us bring it all the way back to something practical. Someone says our LLM service is slow. With everything we have built, that sentence is now way too vague. And that is a good thing because it means you know what to ask. Is the first token slow? Then look at the front of the machine. The queue, the prompt length, prefill, whether the prefix cache is even hitting. Is the streaming slow? The tokens coming out unevenly? Then look at decode, the KV cache size, memory bandwidth, whether a big prefill is interfering, or is the throughput just low overall. Then it is almost always the KV wall, memory capacity, the batching policy, fragmentation, and that is also why you can never measure this with one number. Tokens per second is too blunt. Prompt tokens and output tokens are different currencies. You have to watch them separately, along with time to first token, time per output token, and how full the KV cache is. There is no single best setup either. Tight first token latency, smooth streaming, high throughput, low cost. These fight each other. It is always a trade off for your specific workload. So let me tie the whole thing together. When you send a prompt to a model, the server is not really running a model. It is scheduling a growing memory object. Prefill reads your prompt and builds that memory. Decode reads it again and again to write one token at a time. And almost everything else, continuous batching, page blocks, chunked prefill, prefix reuse, is the same fight over and over. Keep the GPU useful without running out of KV cache. So the next time the first token is slow, you will not just say the model is slow. You will know to ask which clock, and that at high level is the whole game.